Okay, hi. Welcome back to the Physics 1108 lab videos. Today we're going to be doing a lab about waves. And waves are sort of mysterious objects. They are things that aren't nearly as real looking as matter, and yet they turn out to be just as important in a physics view of the universe. Waves are really just disturbances in some sort of medium, meaning that you have some big extended thing and there's a pulse of some sort traveling through it. Now, the best example I know to start people with is the wave in a football stadium. If you have a big football stadium with 100,000 fans and they all do the wave, what's going on? Well, each and every person is just standing up when it's their turn and then sitting down again. And what happens from the outside, looking at this whole thing, you see this big wave propagating around the inside of the stadium. And if you have an oval stadium and a good crowd, it can go around 2 or 3 times. It can be fairly fun. It's actually very impressive that these things happen. Let's think about it physically. What are these people doing? Are they moving along with the wave? No, they're just standing up and sitting down. They're not even moving in the same direction that the wave goes. The wave goes sideways and they're going vertically. The wave is moving quite independent of the motion of anybody involved in it. Nobody in that whole crowd is moving with the wave, and yet the wave is clearly there. It travels around the stadium. You can see it. It's huge. It's a big thing. This is what waves are like. There's a medium, which are the fans, and those things basically stay in one place. They move a little bit, but they essentially stay in one place. And then there's the wave, which is the disturbance, and that moves independently of the medium. The medium stays in one place, the wave travels. That's the big secret about waves. It's very easy to get these two things confused. Don't. They're separate. They do different things. Eventually, it will turn out that waves are just as real as the particles they travel through. They can carry energy, they can carry momentum, they can carry angular momentum. They're just as real as the matter. And that was a big surprise when it turned out. They certainly don't look as real, but they are. And we're going to start talking about them today. We will continue getting back to waves through the rest of the course. It's basically half of what physics does. So, to review, when you're talking about waves, there's a wave disturbance and there's a medium. They do different things. There are many ways to classify waves, one of which is the longitudinal transverse distinction. And a transverse wave is where the particles in the medium travel perpendicular to the way the disturbance goes. In a longitudinal wave, the particles of the medium travel in the same direction, same dimension as the wave disturbance goes. One example of a longitudinal wave is sound. Sound is a wave propagating through air, and what happens is the air particles move a little bit back and forth like this, and as they do that, the wave disturbance moves in the same direction as the air molecules are going. Another example is a slinky that we'll play with in a minute. A transverse wave is what you find in a rope. If you pick up a rope and you snap it at one end, there's a wave disturbance that goes this way, goes up and down. The disturbance moves that way. The medium particles are oscillating up and down. That's a transverse wave. All right, that's the introduction. Now we'll get to some actual equipment and have a look at how a slinky has waves. Now in your lab kit, you should have a nice metal slinky, nice one like this. It's just like the ones you buy in the toy store. And the first thing I want you to do is get this out. Mine has been taped to a big solid box at one end, but for this you can just hold both ends. And we're going to make a wave disturbance and watch it go. So here we go. To make a wave disturbance, all I do is move one end in and out again pretty fast, and that makes a pulse that you can see travel down the slinky. There we go again and again. Okay, so they go down, they travel through the slinky, and as they travel, this pulse propagates. Now notice that the pieces of slinky are not moving very much. They jiggle back and forth a little bit, but nowhere near as much as the wave disturbances. It starts over here and it goes all the way down here. It goes a long ways. None of the slinky is doing that. The motion is all the disturbance. It is not the medium. We can easily figure out what the velocity is with a stopwatch and a ruler. Here's my ruler. It's just a yardstick. And if I measure the distance from the end here down to where my hand is, that's about 36 plus 8, 44 inches. How long does it take a pulse to go from my hand to the box? Well, we can do that with the stopwatch. I'm going to hit start when I make the pulse and hit the same button again when it gets to there. And we'll do it 3 times just to be sure. So here we go. 1. That was 0.8 seconds. 2, also 0.8 seconds. And also 0.8. So I get 0.8 seconds to go from here to here. That's 44 inches. We can use those to find out what's the velocity of the wave. V wave is 44 inches divided by 0.8 seconds. We can turn that into metric, and then we'll have a velocity in meters per second. Okay, it turns out that if you have one kind of medium like this slinky, and it runs into another kind of medium like the box, which is radically different, then you will get a bounce wave back again. So the wave disturbance will go this way, then it will bounce off the end and come back. Now as it goes, it gets smaller and smaller, mostly due to friction with the tabletop. This is clearly diminishing the wave as it goes. But if I make a big one, we should be able to see a wave go down through the slinky, bounce off the far end, and come back again. And here we go. I'll do it again. Some of those were clearer than others, but I could see a bounce 2 or 3 times. I want you to try this until you can see a nice bounce and convince yourself that it really happens. This is part of being a wave, is that waves bounce off boundaries, they reflect. We'll be using this over and over when we get to something like optics. We talk a lot about waves reflecting and exactly what happens when they hit a boundary. Okay, that's it for compression waves. The next thing we're going to do is have a look at a string wave, a standing string wave, and I'm going to have to set up some more stuff for that, so we'll be right back. We're back, and now we're going to talk about another kind of wave. The Slinkies were all about compression waves, with waves that go back and forth the same way as the wave is propagating. The book calls those longitudinal waves. Now we're going to be looking at transverse waves in which the medium is moving perpendicular to the direction the wave is traveling. This is like the wave in a football stadium. The people are moving up and down, and the wave goes sideways. These two things do not have to be the same, and it's perfectly okay for them to be different. Sometimes you get both types. If you look at what the earthquake people do, they deal with two very different kinds of waves that travel at very different speeds. And as a matter of fact, by timing the interval between when the two waves arrive at their sensor, they can tell how far away it was. So let's talk about transverse waves. What's this about? Well, the basic idea is a wave in a string. We have our rope here, it moves up and down, and the wave goes that way. How does the physics of all this work out? Well, in your book, you'll find a derivation for the velocity of a transverse wave. And the velocity of a transverse wave depends upon the tension in the string. It also depends on the mass density in the string. Mass density is just the mass of the whole string divided by its length. So you wind up with something in kilograms per meter for mass density. Now, by changing these things, you can change the velocity of a wave. The formula turns out to be that v equals the square root of t over mu. Now, where can you see this happening? Well, probably the best place to look at it is in a guitar. In a guitar, we have 6 strings in a standard guitar. The strings make different notes. The way they make different notes is they have different velocities for waves in the string. Now, there are a lot of weird things, there's a lot of constraints about a guitar. First off, all the strings have to be the same length. They cannot have an extra long string and a short string. Guitars just aren't made that way. Pianos can do that, but not guitars. The other thing is that the way a guitar is built, you really want all the strings to be roughly at the same tension. Not precisely, but something close. And that's because if one of the strings was at a much bigger tension than the other ones, you'd have a lopsided pull on the neck, and your guitar would eventually warp and stop being playable. So you have to have the same length and the same tension, more or less. I mean, you adjust the tension with little turning knobs, but those two things have to be sort of the same. To get different notes, the only thing left to change is the mass density. And if you look at a guitar, you will see that the different strings are made very differently. The higher strings are really thin wire, and as you go down through the guitar, the very lowest strings are really, really thick wire. And that's just because that way you can have all 6 strings be the same length, have roughly the same tension, and get different velocities and hence different notes out of them. In a piano, they do the same sort of thing. The thick strings are for low notes. They're much thicker than the high strings, but they can also change the length. The high strings are a lot shorter in a piano, and all the stringed instruments, violas and so on, have the same kind of constraints. So how does the velocity change the frequency? Every note has a certain frequency. That's just how often the medium is bouncing back and forth in a second. Well, it turns out that that formula is given by this. The frequency of the lowest oscillation is the velocity divided by 2 times the length of the string. So the frequency is it's 1 over the time it would take for a wave to propagate twice the length of the string. When we look at standing waves in our next bit, we'll kind of start to see why that works out. So that's what there is to know about transverse waves. They involve the medium particles moving perpendicular to the direction in that the wave moves. They depend on the tension and the mass density. The velocity of the wave is given by this formula. And if you have a standing wave in a string, its lowest frequency is given by that. Okay, now we're going to do some experiments with waves in a string. But first we've got to talk about yet another distinction waves have, and this is the difference between traveling waves and standing waves. And what's that distinction? Well, the basic idea is that if you have waves in a string that's tied to a wall at both ends, okay, so it's tied to something very large. You can make waves in the middle of the string. They're just disturbances, and that travel down the string, and they travel this way, blah, 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 until they hit the wall, and then they bounce back. And it turns out that if the string is tied rigidly to a wall, when they bounce back, they are going up if they were going up when they hit the wall. So you get this wave pulse now traveling back this way. And you could do that. You would have a little wave pulse that goes zzz, down the string, hits the wall, bounces back. That's a traveling wave. The wave is actually moving and going somewhere. That's one kind of wave. There's another kind of wave. And this wave is what you get if you have a string. And instead of having a little pulse that goes from one end to the other, we move the whole wave like that. And what happens with this? Well, if you have a wave like this, there are 2 ways to think about it. One is that this disturbance goes down, reflects off the wall, and comes back, and this one goes this way and bounces off that and comes back. The other way to think about it is just that this bounces back and forth like that, and this one bounces back and forth like that. And so you get the whole string doing something like this. Boing, 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 boing. This is known as a standing wave. This is a wave that doesn't go anyplace. It only happens when you have hard walls on either edge. And it just bounces back and forth. This is the kind of wave that the guitar string has. This is the wave most musical instruments are aiming at. You just bounce things back and forth. This isn't the only standing wave. There are others. This is just the easiest one to draw. You can draw another one that looks this. Instead of having 2 lumps, it just has 1. And this goes back and forth like so. This is actually what a guitar string mostly does. Most of a guitar string oscillating is like this. There's a little bit of that one. And there are many more. You can have standing waves that have 3 lumps, 4, 5, 6, whatever. These are different harmonics, they're different frequencies. It turns out that the note these things make, if you call this note of a guitar string the fundamental, then this will be 2 times the fundamental. That will be 3 times, and so on. And these notes you can calculate from the velocity. Remember, the velocity of a traveling wave in a string is given by t over mu. Well, the frequency of the lowest note is v over 2L. And the next one up is V over L. And so on. What we're going to do with our little demonstration here is set up a string, and we'll be able to see it oscillating in the fundamental, and we probably hit the second. If you practice with this, you can get the third. The fourth is really hard to do. We have YouTube videos of people who can hit 8, 9, and so on, and they are pretty amazing devices. Theoretically, there's no upper limit. It could go as high as you want. This is the way standing waves are. All right, now let's get the equipment out and come back in a minute. Okay, here we go. This is some equipment we had sitting around in the lab. This is a piece of rope, and it's tied to a support. We're not going to try and measure anything with this lab because I don't know how to measure the tension I'm putting on this very well. What we're going to do is try and excite this rope in a way to exhibit some transverse waves and standing waves. So if I just hold the rope like this and then give it a little pulse, there is a pulse that travels down, bounces off the end, and comes back to me. However, it's moving so fast that it's really hard to see. If you look on YouTube, you can find people have much longer ropes and better tension. And we can, however, do a decent job with standing waves with something this simple. To make a standing wave, remember, you're going to try and make a wave that just goes up and down. We'll start with this one that looks kind of like a jump rope wave, and I'm going to make it by rotating my hand in a circle instead of up and down. That's just because it's kind of easier to do things this way. And there we go. That's a nice jump rope wave. It has one big node in it that's going up and down. The particles of the media are moving back and forth transverse to the way the wave would be going if it was going anywhere. So there we go. It's a nice fundamental node standing wave. And you should be able to find a piece of rope and make that happen fairly easily. Getting the next one up, this 2 lumper, is a little more difficult. You have to go pretty much twice as fast. And there, I finally got it. Takes a while to get it started. Once you get it going, it works fairly well. You can see that the center of the rope is not moving nearly as much as it is in the 2 nodes. If this was a guitar string, the note that you hear from that one would be twice the frequency, which is another way to say an octave above the note from the jump rope node. And this is the fundamental. This is the first harmonic in musical terms. We can go further up. I can't get it to work. Oh, almost. Maybe you can get a 3-humper to work. If you can, congratulations. You're getting this node. On the YouTube videos, we have people going up further. So there we go. That's all I want you to do this week. This is kind of a qualitative lab. I just want you to set up these things about waves and make them happen and observe them. Next week, we'll get back to a lab with actual numbers, but that's it for today. Bye.